All right, folks, it's 10 minutes afterward, so let's get started. Welcome. Welcome back to the Path Seminar Series. We're reaching the end of the semester here at UC Berkeley, very exciting time. We had Cal Day over the weekend, so the campus was filled with families and prospective students. Graduation is right around the corner, a time to celebrate. And something I'm very excited about right at this moment is the new engineering center had a ribbon cutting yesterday and actually just came from an event inside. I think it's gonna open May 1st officially. So if you have a chance, pop in there. It's absolutely fantastic. Our current dean has done quite the mic drop moment with, fundraising, making everything happen for this new building, and then, right upon her departure, having this grand opening. So anyways, past seminar series, we have another one next week, and then I think our last one is the week after that. But for this week, we have Dr. Mingyuan Wang, who who is a postdoc in PATH and actually has been involved in PATH for some years, including as a PhD student working with Dr. Xiaoyun Liu. Also, I think working actively with Hal and Anthony. I think you worked with them as well. At least I see your guys' name on publications together. And I know you've been working on Connected Adaptive Cruise Control, among other things, and really excited to have you share your work with us today. So let's all give a hand and a warm welcome to Mingyuan.
Thank you, everyone. Today, I'm going to share some research about a current project we are working at CACC, and it's about the Cooperative Adaptive Cruise Control, which is CACC, CACC model, and its application in microscopic simulation. So first, I would like to give a brief introduction about our field data collection efforts that we conducted at ACM, which is the American Center for Mobility, last September and October in Michigan. And we spent 5 weeks there to collect a bunch of trajectory level three test vehicles data under a variety of types of driving scenarios. And for this subtask, the date that I'm going to use is October 23rd and the 24th. The three test vehicles include three types of different powertrains. The leading vehicle is the Toyota Camry, which is a gasoline vehicle, and the second vehicle is Toyota Prius, which is the hybrid vehicle. And the third car is the Nissan Leaf, which is the electric vehicle. And the variables that we extracted from those cars in our database for this modeling work include timestamps, speed, the reference speed and the measured speed of each of these vehicles, the desired and the measured gap of each between every two consecutive vehicles, for including both the time gap in unit of second and the distance gap in unit of meters. We also include some control mode and the braking information included, including like the control mode variable, which indicates that whether this vehicle is currently under human-driven mode or a cruise control mode, adaptive cruise control, or cooperative adaptive cruise control mode. And also we include some braking information, like whether this vehicle is under the automatic driving mode or it's the braking pedal is manually pressed. So those information can help us to determine which exactly driving scenarios this car is currently under. And based on this data, we categorized the driving scenarios into 4 groups. First is the regular CACC car following without any longitudinal or lateral disturbance. The second is the cut-in, cut-out maneuvers. We have a fourth rental car just made those maneuvers in front of each of the 3 test vehicles. The third is the automatic emergency braking, which means that the leading vehicle can have a dramatic, strong deceleration with the help of our automatic program. And the last one is the manual emergency braking, which means that the leading vehicle, the driver in the leading vehicle can manually and hardly brake and press the braking pedal. This is the sample data we extracted from our data set, and these are the speed profiles. And the top two are the regular car following and the cutting cutout scenarios. The bottom two are the emergency braking for automatic and manual emergency braking. So, so to fully utilize those data, we need to develop the model for a microscopic simulation purpose. We first need to develop a CACC car following model framework. And this modeling framework can be implemented in microscopic simulation. In our project, we are using the simulation software Amazon. So we need to basically created a bunch of different trigger conditions to determine whether this vehicle is gonna under the normal cruise control mode or ACC mode or CACC mode. And also under CACC mode, as I just mentioned in the last slide, we have 4 different categorized driving scenarios. So we need to determine whether this CACC driving vehicle is gonna under which scenario based on the braking information and also the distance information, distance gap information with the preceding vehicle. Oh, all right, so those are the key methodologies that we're gonna use in our project. So this is the regular car following model structure that I propose without any longitudinal or lateral disturbance. So basically we can see that it's a two-layer method. First, we need to calculate the distance gap change between the preceding vehicle and the subject vehicle. We also gonna take the speed difference of the preceding and subject vehicle into account, and then utilize those gap arrow and the derivative of the gap arrows to calculate the reference speed of subject vehicle. And then we utilize the reference speed of subject vehicle and the difference between the reference speed and the measured speed of subject vehicle to calculate the recommended acceleration and utilize the recommended acceleration to iteratively update the vehicle dynamics, basically to tell the vehicle what's the speed or what's the acceleration that it's gonna take in the next time step, and then so on and so forth. So that's the regular car following without any disturbance. But for the emergency braking, because the behaviors are also gonna be quite different. So first we have different trigger conditions. So basically it's like based on the speed or some other information that we can get from the data set, we need to first determine whether this vehicle should under the emergency braking. And if it is a yes, then we need to take a different equation formula to calculate the reference speed of the subject vehicle. And then we need to the other formula is just the same as I showed in the last slide, like how to calculate the gap arrow or how to apply the gap arrow correction to the formula is just the same. The main difference comes from the way to how to calculate the reference speed of the subject vehicle. And after we activate emergency braking and finish that, we need to apply a smoothing transition, basically to give a boundary of the reference speed to these CACC vehicles to make sure that this vehicle will not take a very aggressive or too conservative behaviors so that it can smoothly transit back to the regular coupling after the emergency braking has been finished. So this, when I fit our model, I just proposed to the data we collected at ACM. So you can see that because the Camry is always the leading vehicle, Prius is the second, and Leaf is the third. So we're gonna need to have different optimal parameters fit to both the second and third vehicle. And we can see that the parameters are different, and as well as the root mean square error. This is the root mean square errors between the simulated speed profiles and the observed speed profiles. So the smaller this error is, which means that the better the model performance it is. And in the regular car following, we can see that the error is both of them are controlled under 0.2, and also the second vehicle also has a smaller root mean square error compared to the third vehicle. So this is the manual emergency braking case. We have separate parameter sets to fit to the data, because under the manual emergency braking, we can see that it has a dramatic overreaction, especially for the second vehicle, which is Prius, because it needs to take such a conservative and overreacted reaction to avoid the collision. And the room square error for the model obviously gonna increase compared to the regular case. For the automatic emergency braking, which means that the subject vehicle can still get access to the reference speed of the leading vehicle. And in this case, while the parameters keep the same, but the fitting performance becomes much better compared to the manual case, and the room square error becomes much smaller. So for the cut-in and cut-out scenarios, so first we need to finish the recalibration of the regular car following, and then have the smoothing functions from the emergency braking to the regular car following, and then we separate the cut-in, cut-out maneuvers into 3 continuous mode. I call it before lane change, which is the preparation stage, and then during the lane change, which is the receiving lane change, car following, and then after lane change. So that's what I call BCF, RCF, and ACF modes. So we have a trigger condition here. Basically, it means that if the subject vehicle has a dramatic change of the distance gap with the preceding vehicle, it means that the following object changes within a short amount of time. That means cutting or cut-out maneuvers happen. And then based on whether this difference in terms of the distance gap is positive, has a positive sign, or a negative sign, we can determine whether it's a cutting or cut-out. So for cutting, to avoid any too strong or aggressive behaviors at the very beginning, we apply a 2 seconds open loop phase, which means that it could apply a very conservative car following behavior to avoid any potential risk of collision, and then followed by a dynamic target speed constraint for the next 2 phases. And for cutouts, it's just we're gonna apply a very similar strategy as we applied to our previous ACC mode, which is to apply an increase the desired time gap after the lane change is detected. So the car will not automatically have such a strong acceleration to catch up with the preceding vehicle, because with the cutout, the vehicle the distance gap gonna dramatically increase. So we're gonna apply a dynamic desired time gap first to avoid any too strong and aggressive acceleration. So after we implement all these models, as well as the smoothing algorithms implemented into our micro SDK codes written in C++ in Amazon, we're gonna testing those models' performance in the latest Amazon 24. The 2 networks that we are using includes, first is only a freeway corridor, includes just the highway is the SR99, and the second is the US 101 SR82 freeway and arterial network, including both 8.5 mile long freeway and parallel arterials connecting with each other. So we start our just for your interest, this is not the focus of this project, but it's also part of my previous PhD dissertation. We developed some other ACC car following models before, and those models have been published in some conference papers and journal articles. If you are interested, you can always easily get access online for these models. But here I just quickly go over these ACC models, because if we want to test and evaluate the CACC performance that we just developed in this project, we also need a pretty accurate and reliable ACC models. And these are the ACC models I developed previously. So it also needs to be has separate models on the different driving scenarios, and also for different powertrains, like ICE engine vehicles and EVs also has quite different drive coupling behaviors that need separate models to capture. And also when it comes to cutting cutouts, it also has separate models to respond to those cutting cutout maneuvers. All right, let's jump to our simulation results with all those ACC, CACC models on the different powertrains. First, I didn't add those CACC vehicles, just go with ACC vehicles, but with different powertrains. We gradually and incrementally add the market penetration of the electric vehicles paired with ACC. So first, we tested 100% ICE engine vehicle activated with ACC, and then gradually increased the market penetration of EVs, and eventually we get the 100% electric vehicles paired with ACC, and we look at the total travel distance, the speed, the Q spearback speed, the average headway, those very classic and representative traffic performance metrics. And the results that we can get from the simulation is that if we transfer from all the ICE engine vehicles to electric engine vehicles while activating ACC the whole time, the discharge flow and the total travel distance is going to increase by over 20% respectively, while the average headway downstream the major bottleneck on this freeway corridor going to decrease by about 18%, which is quite consistent with our field observations of those two powertrains paired with ACC.
In these simulation results, there's no cut-in or emergency braking.
No, yeah, this one is no, but the other simulation that I'm gonna show in the next slide that include those emergency braking.
Since you're gonna include those in the next slide, can I also ask, what is, before you've done this work in considering cut-ins and emergency braking, what is the state of the art in the literature? Has that been considered in the design and analysis of CACC?
Oh, yeah, sorry, I need to clarify that. So for ACC, it does not include the emergency braking, because if you have an emergency braking, it basically just switch back to the manual driven mode. It's just behave like a human driven vehicle.
Yeah.
And for cutting and cutout, actually we have the cutting and cutout, how the ACC gonna handle cutting and cutout in our models.
So my question remains though, what is the state of the art in the literature before you started to design CACC for cut-in and cutout emergency braking? Are there articles in this already, or is this completely new? Nobody's studied this before.
It's quite new. It's very new. So there was some research analyzed the cutting and cutouts for human-driven vehicles, but for ACC and the CACC, most of the researchers just stick with the regular coupling without any lateral movements. Like basically, it's just in a platoon, each vehicle just follow another one and analyze like the longitudinal control without any lateral movement. So it's quite new. But I just follow some ideas from the studies of the lane change behaviors for human-driven vehicles, and we borrow some of the ideas, and then also created some new ideas just to integrate them together for ACC and CACC.
Cool. Yeah, please highlight those particular things.
Okay,
You want to appreciate those.
all right. Yeah, thank you.
I think you're talking about traffic simulation. So in traffic simulation previously, it's rarely considered cutting emergency braking for ACC or CACC models. But Scott, I think your question is more related on vehicle control design. And for vehicle control design, of course, ACC and the CACC traditionally consider cutting. They have to consider cutting, cutout, and emergency braking.
I see.
Right. So this research mainly focused on a simulation-based car volume models. So basically, it means that the ultimate goal is to help the simulation to simulate or mimic the real-world car volume behaviors as much as possible. So that's the ultimate goal to develop the simulation-based models. Because, for example, we cannot, for human-driven vehicles, it's pretty easy to observe those vehicles behaviors that just use either loop detectors or like those dash cameras just installed along the road. But for ACC or CACC, for example, if I want to say, if all the human-driven vehicles on freeway gonna be replaced by 100% CACC or ACC vehicles, what's the traffic benefit it can bring? And those studies, we cannot use the field test to evaluate that. That's why we need to use the simulation software to simulate and evaluate those performance. And that's when those simulation-based scaffolding models need to be applied. Yeah, so, and then this is the sensitivity analysis for those ACC scaffolding behaviors. The left plot is basically just I manually increase the market penetration of the electric vehicles, and then the discharge flow and total travel distance gradually increase. The right plot is that if I gradually increase the RAM metering rate, so basically it means that if more vehicles coming from RAM metering, and we know that if more vehicles come from the RAM metering, it means that more lateral movements gonna be observed on freeway as major bottlenecks. And those lateral movements if more lateral movements observed in the simulation, which means that our cutting and cutout scenario, the receiving lane change scaffolding models gonna be applied more frequently. And in this case, we can see that for ICE vehicles, it's very sensitive to those lateral movements. Any small lateral on-ramp demand can trigger a pretty obvious capacity drop and negative traffic benefits. But for electric vehicles, you can see it's more robust and it's not that sensitive to those on-ramp demand increasing compared to ICE engine vehicles. And only as the on-ramp demand increase up to 600 vehicle per hour per lane, you can see a pretty distinguished drop in traffic performance.
What's the explanation for that? Why are EVs performing better according to these metrics?
Yes, that's a very good question. It's basically because it has a faster response of the ACC controller for those electric vehicles. It has something, and it also has something with the powertrain characteristics. So for ICE engine vehicles, it's like when the speed is lower, because basically when the traffic is congested, we're gonna encounter those low speed. And when the traffic is on the low speed, the power of those ICE engine vehicles is also lower. But for electric engine vehicles, it actually has a consistent power. So even under very low speed, it will not have like a much lower power compared to those high speed scenarios. While giving those consistent power, it means that it can have a stronger and faster response to the preceding vehicle. So the gap between the subject vehicle and the preceding vehicle can be much shorter compared to ICE engine vehicle. Basically, it means that the EVs can easily catch up with the preceding vehicle, even under very large speed fluctuations. All right, so after we analyze some basic properties of the ICE engine vehicles and the EV paired with ACC, we add CACC vehicles into consideration. So the first column is the market penetration of the CACC, and once we determine the market penetration of CACC vehicles, the remaining market penetration gonna be shared between the electric vehicle paired with ACC and ICE engine vehicle paired with ACC. And these tables are just similar as the table I showed in the last few slides, compared the traffic performance of those different market penetrations. And the general conclusion, so the CACC increased from 0% to 100%. The general conclusion is that as the market penetration of CACC increased, the road capacity can increase by up to 43% compared to the ACC equipped combustion-based vehicles, and by up to 14% compared to the ACC equipped electric vehicles. And the 80% CACC and the 20% electric vehicle paired with ACC could have a pretty similar performance at 100% CACC, indicating the EV capability to catch up with the faster response tuned vehicles. And this is just a graphical way to show all those numbers listed in those tables. So the x-axis represents the market penetration of the EV increases, and different colors just represent the different market penetration of CACC. And you can see basically it's like more EV paired with ACC and more CACC could bring a better traffic performance on both freeway corridor and at a network level. And then after we conducted all those preliminary scientific analysis in the traffic side, I also would like to introduce a little bit about our co-simulation works in this project. So basically, previously we assumed that all the CACC vehicles can communicate with all the other CACC vehicles without any failure communication, which means that they can always get access to all the other CACC vehicles information during the whole simulation. However, that's not the real case. So our cooperation team from Unreal, they develop a V2X communication model. Basically, they tell us that each CACC vehicle has a particular percentage or probability of failing to communicate with other CACC vehicles. And if this situation happens, which means that this car cannot communicate and it will switch from CACC mode to a normal ACC mode, and the performance will become worse. That's also a key component of this project. So the methodology that we tested for this co-simulation include basically two parts. We first start from a static method, and then we move to a dynamic method. So the difference between a static method and the dynamic method are included in these two flowcharts. So for static method, basically, we just run their V2X communication models offline and get the results before our microscopic simulation even begins. And then we get the outputs of their communication models and load them at the beginning of the simulation, and then use those outputs to determine each vehicle, whether this vehicle travel at each freeway section, it can maintain under CACC, or it will switch back to ACC due to a failure of communicating with other vehicles. However, for dynamic method, it's gonna get update at every simulation step. So basically, it's like at every simulation step, we're gonna get every simulated vehicle's coordinates, and then pass those vehicles' coordinates to the V2X communication models. And the V2X communication models gonna output a packet reception rates. And we're gonna utilize those packet reception rates to determine at this particular time step each vehicle, whether it can receive the message successfully or not. And based on this condition, we're gonna determine each vehicle is gonna maintain under CACC mode, or it's gonna go back to the ACC mode. So these are the package drops under different CV traffic demands. So basically, it just provides a basic understanding of like what's like on average these package drop rates in a pretty representative freeway networks. Basically, our understanding is that the higher density the freeway is, and then the higher probability this vehicle could drop messages. And we can see that we tested this performance under the traffic performance from a medium level traffic to a heavy level traffic, from 7,000 vehicles per hour to 10,000 vehicles per hour. And we can see that the package drops increase from 2.2 to 5.2. And
that's experimentally collected in the field, or this is just simulated?
These are simulated. So our collaborator, the Unreal team, they develop neural network-based communication models on their side, and we just directly apply their communication models in our simulation. We just directly tested their communication models performance in our simulation under different traffic demands.
Are we assuming each connected vehicle can potentially connect to every other connected vehicle? So it's like a 1-to-N?
Yes, yes.
Okay. And so there's this Bernoulli distribution for the pairwise connection, or between one vehicle I and one vehicle index J, or it's vehicle I and all other vehicles?
All the other vehicles. That's
So, okay, so if it's beyond the threshold, then it can't communicate with any vehicles?
yes, that's correct. Then people will switch back to ACC. Basically, it's just gonna follow the preceding vehicle.
And are there any distance constraints for communication?
Yes, I'm gonna discuss later. So
Okay.
it's gonna be one key dimension in our sensitivity analysis.
I see, okay, okay.
Yeah, basically that's the distribution of those package drops under the different CACC traffic demands, and it just gradually moves from a center at 2% to 5% while the travel demand increases. And the first sensitivity analysis, while adding those V2X communication models, the first thing we did is that if we assume, because their model can only generate, as you can see, a very relatively small package reception rate, like from 2% to 5%, even under very heavy traffic performance, their models can only generate about 5% package drops. But I'm just curious, like what if I just manually put a very incredibly large package drop rates, then how the performance will look like? And these are just, I manually increase the package drop from 0% to even 100%. And then that's the traffic performance. And you can see that the traffic performance can even decrease dramatically while the package drop rates go beyond the 20%. So basically it means that on average, if 20%, over 20% of the CACC vehicles cannot communicate with other vehicles, then the traffic performance will go really bad. But if it's just maintained around 5% or 10%, the performance are still very promising. And then, okay, after give a quick overview of that, I conducted sensitivity analysis, adding these V2X communication models with two dimensions. First is the varied traffic demands, and the second is the different market penetrations. And then in this case, well, you can see that the difference while adding between the scenarios with the communication model and without communication models is just about, even below 2%. The difference is not much difference while adding the V2X models. However, if we increase the market penetration of CACC from 0% to 100%, then the difference will become maximal when the CACC market penetration is about 60%. And the discharge flow and the total travel distance gonna increase a little bit over 2%. But still, the difference is not that huge. But again, it's a static method, so it's not accurate. We eventually gonna move to our dynamic method, which is to literally update and run their communication model at every simulation step. So we need to initialize the helix once at the beginning of the simulation, and this helix is kind of like a connector between their communication models and our driving behavior models. So at each simulation step, we're gonna retrieve the vehicle coordinates and pass those coordinates into their communication model, and then the model gonna return a vector that stores the packet reception rates associated with each section in the network. And then we're gonna determine the driving mode of each CACC vehicle based on the location and the corresponding package reception rate. And then we're gonna iteratively update the vehicle dynamics and repeat from step 2 to step 4. And then these are the potential future sensitivity analysis we're gonna conduct. So alongside the classic and the representative traffic side, which is to increase or decrease the travel demand and also play around with the market penetration of different types of CVs, we also need to consider the communication range. For example, if the communication range right now we set at 100 meters, and then what if the communication range of the CACC vehicles gonna be even larger to 200 meters or even to 1,000 meters? Then activate those vehicle V2X communication models, how this model can affect the traffic performance differently. And we also have two other professional parameters we can play with. which is the probability of the resource reselection and the resource reservation period. Those are the very professional parameters related to the communication models.
Is communication a delay another issue that you consider?
The communication delay actually directly included in our car following behavior models. So it's like their communication models, we directly get their outputs without any delay. But when we run our car following models, it actually has the communication delays. And for ACC, it's about it ranges from 0.4 seconds to 2 seconds, depends on the gap setting. Because for ACC, sometimes you have a short gap setting, sometimes you have a long gap setting. It depends on how conservative or how aggressive you set for the ACC, the delay could be different. But for CACC, the communication delay is pretty low. I didn't really take that into account. But for ACC, yes. Yeah, and then this basically is just what we are still missing and what we're gonna plan to do in the last few months of this project. So first, we need to final testing our code simulation platform with Unreal, and then improve the efficiency of our simulation. For example, the packet reception rate, we're gonna test. Is it necessary to be updated every simulation step, which is 0.1 second, or we can kind of increase it to 0.5 second or even 1 second to improve the efficiency while not losing too much accuracy of the simulation. And also the switch between the CACC and the ACC logistics could also be reconsidered in more details. For example, like whether we need to immediately switch back to ACC while the communication drops, or if the communication has a continuous drop for over 1 or 2 seconds or 10 simulation steps, then we switch back to ACC. The second step thing we need to do is, of course, to further adding those cutting and cutouts and also the emergent braking modules into consideration and have a comparative analysis with our previous CACC model to see how the new model has what kind of difference it could bring to the traffic performance evaluation. And then the third step is to, like what I showed in the last slide, to conduct sensitivity analysis, not only from the traffic slide, like the travel demands or the market penetration of different CVs, but also from the communication side, how we play with those communication range and other communication related parameters. And then it's just about annual report and some conference journal article write-up. Yes, thank you, everyone. This is my presentation today. Any questions? Yeah, sure.
This may be out of scope, I'm not sure, but I've always been interested in like mixed traffic with like car following. So how would the model do with, say, a human-driven vehicle were to intercept in the headway? Like, would it adjust, recalibrate, or is it dependent on just the preceding vehicle, or does it adjust whichever it's dependent on?
Yeah, so that's a good question. So for different types of AVs like ACC or CACC, we have an average time gap or the headway we set in the simulation, and it gonna follow a uniform, follow a standard distribution. For example, we set ACC the headway to 2 seconds, and then it has a standard distribution with a particular standard deviation, and then in the simulation when it generates those vehicles, each individual vehicle is gonna follow this distribution of the headways, and it will always try to maintain this headway.
I see. So is the simulation assuming that all the vehicles are connected, or does it also, can you calibrate like they're driven versus like the connected vehicles in the simulation?
So could you repeat?
Yeah, in the simulation, is it assumed that they're all connected with each other?
It depends on the vehicle type, actually. So in the simulation, we have a bunch of different vehicle types, like human-driven vehicle is one type, and then we have ACC, using the ICE engine, and then ACC using electric engine, and then CACC, and then we also have ACC trucks, CACC trucks. The reason we have those separate vehicle types is because in the simulation, each vehicle type gonna associated with a unique ID. And then in our coding, we're gonna determine if this vehicle has this particular unique ID, which means if this vehicle belongs to this vehicle type, then we're gonna apply a different car following models to this specific vehicle type.
So for the car following models, sorry, I'm stretching back here a little bit, can you describe a little bit how you guys created the CACC model and how that relates to AIMSUM model? AIMSUM's like based on the Gibbs model, correct? So like the CACC, is that something that you developed totally on your own, or is that something that you built off of the AIMSUM models?
No, so this CACC model actually developed on our own.
That's all, yeah. And then, okay, perfect, that's what I thought. So then that gets a little bit to my second question. I'm curious if you looked at potential heterogeneity in different CACC models, especially looking towards the possibility that each OEMs all are gonna have their own models, they're going to be proprietary, we don't have access to them, but we can estimate that in the future there's going, if this happens and we have the OEMs involved, you're likely going to have a bunch of different, hopefully interoperable, but still distinct CACC car following models. I'm curious, do you understand where I'm getting there?
Yes, yeah, I totally get it. So you are saying like the CACC models could be quite different.
Yeah, I'm curious what if you had any insight into what the impacts of heterogeneity in the CACC models will be.
Yes, that's a very good question. So basically, it's like that's why we have those field tests first, and then we try to develop a model to fit our field data as close as possible. So the field data is like we prove that our CACC controller actually works and it can run safely under a bunch of different driving scenarios. So it's one of the CACC controller that proves to work in the real world. And our model is just trying to fit that data as close as possible. I know you are saying like maybe we can create a bunch of different CACC models to fit to different CACC controller, for example, from different manufacturers, or maybe like, because I know there are gonna be some heterogeneity in those car following models, but the bottom line or the difficulty to develop this model is that we first need those real world data first.
Gotcha, yeah.
Yeah, that's
It's a chicken or an egg issue, yeah.
Yes. But thank you. That's a very good question.
I have one more. I had a follow-up then too. I'm also curious, I'm guessing the answer is no, but I am curious what would happen as you varied vehicle types as well, especially, Xiaoyun's done a bunch of work on heavy duty vehicles and the like, and especially the conversation that you were having just now about one of the reasons that EVs are more effective is their response times are faster and yada yada. I'm especially curious how these sort of CACC models would work in not not Prius platoons, but say truck platoons or something.
Yes, that's thank you. We actually I didn't show it here, but we actually have separate CACC truck models. It's different from these passenger cars CACC models.
Yeah.
Actually, those are we had a previous project actually collected some CACC truck data in the field.
Yeah.
And then we have a separate CACC truck model to fit to those CACC truck data. I didn't show it here.
Yeah.
That's not.
But you have, that's really cool that you do have.
Yeah, thank you. Yeah.
And then my absolute last question is a broad one, is we've been doing this sort of work here at Berkeley for quite some time,
Yes.
right? And we're all really excited about the potential. From your perspective, what needs to happen for us to start seeing real world benefits for CACC, say the next 5 years? Is that even a possibility?
you mean to implement the controller design? Actually, I'm afraid that it's gonna be very hard to realize that.
Why?
Because still, I think the safe concern is gonna be a thing, because when we test it in the field, it's still we spend a lot of time in tuning our CACC controller to make sure it can safely operate under different driving scenarios.
Mhm.
Because sometimes in the real world, it's not just follow a particular speed profiles under very safe conditions. Sometimes you can encounter some very unexpected thing, like a sudden cutting vehicle. That's why we also create like cutting cutout scenarios, because those scenarios can sometimes create some dangerous situation in the real world. So I'm not sure if those things can place in the market in the near future to like 100%, or with a very high probability to safely handle all those situations. That's my concern. Yeah, because if you sit in those cars and conducted all the field experiments, you can easily feel like those systems are not that reliable, like during the whole time. Sometimes it's gonna be dangerous, and we need to manually brake, and then we need to change our coding programs to tune it to yeah, something like that.
Thanks.
Also getting all the OEMs to agree, right? Because it's under the assumption they all have to agree to be connected and to cooperate, right?
Mhm.
With the parameters.
Yeah, I have a preference for parameters with new selected for KVKD and KP. Yeah, and yeah, I remember. So what's the principle for you to turn up these parameters to guarantee the system is input to state stability? This close loop system is stability. The different parameter used. Yeah. Right.
Yeah, so basically I have to say that this model, the reason I developed it in this way is because we have a colleague, Demetrius, who is responsible for developing this controller in the field. And first he tested this controller in the field and proved it works. And I borrowed the key structure from his controller design and borrowed here. And as I mentioned, because it's a simulation-based model, and in our microscopic simulation, it does not include those low-level control. So all we need to make sure is that the simulated vehicles can have a similar trajectory compared to this realistic trajectory. So I didn't really need to take serious consideration about like stability or stuff. I directly borrow the controller design ideas from my CACC colleague. And then I just need to make sure all those functions could fit the data, and the simulation trajectories can be as close as possible to the realistic trajectories.
Any more questions? Not to put you on the spot very Laura, but I'm kind of keen to hear what you think or how you're reacting to. Sorry to put you on the spot, but
No, it's fine.
any questions or insights like that you're thinking of from, you know, the experiments and deployments you've all done?
So there were several things that I think, but I think that most of the main thing that I was thinking about was, I think, and he got to answer the question for me, was how did you end up having this particular car following models, and why did you choose this one? And also, this. So you mentioned that Demetrius is the one who's doing the control, right? And then you took out the control and then you applied it in this particular context with the communication, right?
That's correct.
Okay, but the controller does take into account the communication that you're having?
No.
Is that by design or was something?
The communication model is a separate one that we just separately encoded into the microscopic simulation. But in the real world, the controller, no, because in the real world, we only have 3 test vehicles.
Yeah.
Yeah, one follow each other, but the communication model basically is just whether this vehicle can communicate with all the surrounding vehicles. And those situations could only take place in the simulation, while you have hundreds of thousands of vehicles that happen. And that's when the communication model gonna be. Because in the real world, when we collected in the field, we only have 3 vehicles. So it does not need to be communicated with all the other vehicles. It's just 3 vehicles.
No, I agree with that, but you're still gonna need to use it in the real world at some point, right? So why don't you test it even in the 3 vehicles that you have?
Oh, so the 3 vehicles have the communication capability
Okay.
with each other. Yes, it has.
Okay,
Yeah, it's just, this one is just, in the simulation, this communication model, basically, it's just, help us to detect, whether each model can communicate with each other with a particular failure probability. And those failure probability actually, because those parts are developed by our area colleagues, and they told me that they also need our, field communication data to fit their communication.
okay, but if they are detached, then why do you need a specific CACC model? Right? I can have a control model and then I can have a communication model. I just need to find a way for them to communicate with each other.
Because it's in the microscopic simulation, and in the simulation, it does not have a low level control. All the controls, all the behaviors, are just, controlled in a trajectory level. It's not, it does not have, for example, like a braking system in a simulation
Correct.
of
But
that.
Jameson does that, right?
I don't think so. No.
So the Gibbs model can do that.
Yes,
Okay,
yes.
so why do you need a CAC model? That's not the Gibbs model,
Oh, you mean why we did not use the Amazon default model?
for example.
Okay. It's because, yes, that's, yeah, okay, yeah, that's a good question. It's because the Gibbs model cannot fit our field data.
So you take the field data
Mhm.
and this model can fit it?
Yes, it can fit it. So that's why I say it's like, we trying to, because in the real world, we only have 3 vehicles, right? But in the simulation, we need to simulate thousands of vehicles. So we need to kind of like mimic or replicate all those 3 vehicles trajectory into the simulation to replicate thousands of vehicles trajectories.
You said the Gibbs model cannot fit field data.
It's
Is
not,
it cannot, or you just did not?
it cannot perfectly fit. We have a comparison of a different bunch of vehicle models. For example, like IDM models, like OVRV models,
And this one is the one that fit the most.
fit the most.
Yeah, I'm curious to see that.
Yes, that's correct.
And wait, this you fitted on the 3 people only?
Yes. Yes.
Okay. I'll be curious to see that.
Yeah.
Okay, good. Great team discussion. Let's give a final hand to Mingyuan. Thank you.
Thank you.